Hello, good morning. Welcome to our lecture. I think it almost feels like we've not had a lecture in a long time. I think I wasn't available for the lecture on Wednesday, and then we had a test on Monday. So yeah, welcome. Now, we are going to have a lecture. We're going to continue with the lecture on flip-flops today. I hope that you've had a chance to go through the chapter, to go through the NAND-based flip-flop or NAND latch that we went through. Do let me know if you can hear me, by the way. I might be talking to myself.
Yes, we can.
Okay, thank you. So we had reached, I hope you can also see.
I can hear you.
Yeah, thanks. I also hope that you can see the slides. Now, I'm going to...
Yo!
That is Sewa Good Jade Chinobe. And he thinks he's a student also. Huh? He thinks he's a student. Okay. The last part of the previous chapter, I intend to go back to it. Maybe I will. Maybe next lecture we can start with it. Yeah, okay, cool. That was about troubleshooting. Maybe in the next lecture we can start with it. So let me just recap. Since we've spent a bit of time without having a lecture, let me just recap what we did. We talked obviously about the fact that memory, flip-flops have memory. In fact, I went as far as telling you that some memory devices, in fact, perhaps most of them, are made of flip-flops, and each flip-flop stores one bit. So the state of the flip-flop is actually the bit that is being stored. If the flip-flop has a state of 0, it means it is storing a bit of 0. If it has a state of 1, it is storing 1, bit 1. Now, sometimes in our circuits, we combine combinational circuits, which are the ones that we've been looking at, with memory elements to create outputs. Okay, so we'll be combining flip-flops with actually combinational logic circuits. The combinational logic circuits are those whose output depends on the current state of the inputs or the current states of the inputs. Whereas with flip-flops, sometimes you might have inputs that do not actually affect the output, which is the memory concept of the flip-flop. And we said that the state of, okay, so we have two outputs out of a flip-flop, the normal output and the inverted output. They are just opposite of each other. And when I say the state of the flip-flop, I mean the Q state. The Q state, the normal state, is the state of the output. So if I tell you that the inverse or the inverted output is a 1, I'm inadvertently telling you that the state of that flip-flop is actually a 0. Then we said that we can, when we first actually start a flip-flop, it can come up in whatever state. It could be a 1 or it could be a 0. But sometimes we want to ensure that it is a 0 or a 1. When we want to make the state of the flip-flop a 1, we set it. Okay, so we say we are setting the flip-flop. That means we are forcing it to get a state of 1. If it is already in a state of 1 and we set it again, it just simply remains in a state of 1. If we want to force it into a state of 0, we say we are resetting the flip-flop. And if it is already 0, that means it's already reset, and we reset it again, it just simply remains in that state. Resetting is also the same as clear. So I can say that a flip-flop is initially cleared. And then I continue with a question. That basically means that I'm telling you that initially the state of the flip-flop is 0. Q is 0, Q inverse is 1. Right. And then we looked at the NAND gate latch, where we said that actually the outputs are cross-coupled to the inputs, and then you have your reset input and your set input, and these reside in one. They are usually one, and we know what we do when we want to make them a 0. So if we want to set, that means we want to change Q to a 1, we momentarily move set to a 0, and we keep reset in 1. And when we do that, even when we put back the set input to a 1, the output will remain a 1. So that is how we set. And that is the same whether the Q was already set or not. If we want to reset, we keep set at 1, and we move the reset momentarily low. That actually makes the inverted output a 1 and the normal output is 0. And that means we have reset, or we have cleared the flip-flop. So that means really that these two inputs, set and reset, perform their functions when they go low. So we can actually say that they are active low. Brinton, please. So they are active low. So that means we keep them in a high state. Okay, we keep them in a high state ordinarily when we are not trying to set or reset. We keep them in a high state, because if we put them in their active states, which is the low state, then we are going to be either setting or resetting. We looked at the truth table, and this is as long as they are 1 and 1, there is no change, because we are neither setting nor resetting, so the output prevails. If we make set a 0, that will set our flip-flop. By setting, we mean the Q output, or the normal output, is a 1. If we reset, that means we are making reset 0. We are clearing the flip-flop. And we say that when we try to set and reset at the same time, that is an invalid combination of inputs. You don't want to set and reset at the same time, because, I mean, what are you trying to achieve? You're trying to produce that, yet we know that one should be an inverse of the other. Great. Yeah, so that is where we were. We looked at an alternate representation, because if you do, we already know that these are active low anyway, but if we use alternate gates, we saw that we end up with this, and you can draw your latch symbol like that, where the bubbles mean that these inputs are active low, and the outputs are whatever they are. They are not really active low. It depends on what is connected beyond that. Good. So here we have a system that is initially cleared, meaning Q is 0. And they want you to complete the waveform. So if it is 0, now with this one, we are looking for either set or reset. There is no point looking at other states, because there are no other states. We are only going to have a difference at the output if we either set or reset. So you're looking for the points where the set or reset values actually go to 0. They go momentarily 0. So you can see at this point, our reset goes low, meaning that it is active low. So it should actually clear the flip-flop. But the flip-flop is already cleared, so we stay in the state 0 until we reach this point where we set, right? The moment we make set 0, you can see they are active low, they have bars. Now we are setting, meaning we take it high until the next set. So it will remain until the next set or reset. We know that will remain, the state will prevail. Here we set, meaning that we remain in the high state until this point where we clear again and we go 0. So then we looked at the bouncing, the mechanical bounce, or the contact bounce phenomenon, where you produce these sort of signals as the switch is trying to actually settle down on the contact. The terminals are settling down to remain in contact with each other. You get those signals, and in these small circuits, those signals can actually bring problems. So if you implement this mechanical switch using a flip-flop, the moment the first contact is made, the switch will remain in the high state, even though the contacts are touching and releasing until they settle down. But remember, because of the memory capability of the flip-flop, it will continue to output the same Q output, V out of 5 volts. So we looked at that, and then I think this is where we were supposed to go, the NOR gate latch. So the one we've been looking at is really the NAND gate latch. These work essentially the same. So I've not put the detail of resetting and setting. Now we can move on to just looking at the truth tables, but they work essentially the same. We will see that the functionality is the same, but the outputs, of course, are a bit different. Otherwise, they would be the same. So you have a NAND gate latch, a NOR gate latch. This is a NOR gate and a NOR gate, and we cross-couple the outputs with one of the inputs to each of these gates, and then you still have your set and reset. What we need to see here is that now these are active high. Before, in the NAND gate, they were the NAND gate latch, they were active low. Here they are active high. So that's really the only difference. The 0, 0 state gives us no change. The 1, 1 state is invalid because if they are active high, it would mean that in 1, 1 you're trying to set and reset at the same time. So that is invalid. And now in the NOR gate latch, for us to set, we actually momentarily move the set input to a 1. So if they are active high, they are kept low. Their normal resting states are low because you only remove them in their active states for you to perform their active function. And if we want to reset, we move the reset input to a 1 while keeping the other one as 0, and we reset and we set. So, and because now these are active high, you can see that we've lost the bubbles. No bubbles at the input. However, the outputs remain essentially the same. So we can say we can also call this the SR latch. In fact, we usually say S and R inputs. This means, these inputs mean the set and the reset or the clear. Reset also means clear, okay, input. So we can, if I in future say SR flip-flop, even in this lecture, we are going to see it. SR flip-flop, I'm essentially referring to the NOR gate latch, okay. Now, let us look at this example. We are going to assume that Q is 0. Obviously, we know that for us to set S is equal to 1, R is equal to 0. For us to reset, S is equal to 0, R is equal to 1. So that's what you need. The other one is when S is 0, R is 0, this one is no change. And no change, you can call it Q naught, just to say that actually the Q, the initial Q sort of prevails. Q naught not being like time, a time thing. So anyway, so we are interested in these positions where we can set or we can reset. So we have that. Here we could reset, these ones don't matter when we come back down because we know that no change. Then here we reset again, and then here we set again. So if my Q is 0, that is Q, that's 0, 1. If I'm in 0, the moment set goes high, I will set, right? And then I will remain in the set state until I'm cleared or reset. So at this position, you can see that you reset and you will remain in that state until the next set. So even a reset doesn't change, because it just resets again. And so at this point, we will still remain at 0 until we set again, which is at that point when set goes to 1, and we will remain with set. So you remain set until you are reset, and you will remain reset until you are set. It is as simple as that. So that really makes things quite easy. Please remember, if you have any questions, put your hand up or text, do in the chat, and I will answer your questions. And you can see this is the correct, which is similar to what we have, okay? Yeah. So we had already seen the waveforms for the NAND gate, and with the NAND gate, it was the same. Once you are set, you will remain set until you are cleared, and once you're cleared or reset, you will remain in that state until you are set. So it's really quite simple. So okay, there's a question. Exactly, Musa. This is the opposite of the NAND gate. If you look at their truth tables, it is essentially the opposite of the NAND gate. But I think you will usually find the NOR gate latch being used. Certainly in most of the questions you'll meet, you'll find it's usually the SR or the NOR gate latch that is being used, but they are essentially opposite of each other. Obviously, for me, I'm at liberty to bring either the NAND gate latch or the NOR gate latch. Okay, so please read both of them. Our outputs arranged as that. I don't know what you mean by our outputs arranged as that. You may want to do a follow-up on that, Isham, and I'll be happy to answer. Anena complex. I don't know what you mean by complex.
Good morning.
Good morning.
I was asking the outputs arranged like that because I'm seeing we have our Q below here, and then we have the Q inverse up, but then on this symbol, we have our Q adjacent to S.
On this thing, yeah, they are arranged like this. So in the NOR gate latch, the other difference is that now the Q, the inverted output is this, the normal output is down here, which is different from when we saw here where the inverted, but the latch is the same. The symbol is the same. The Q can be up or down. It doesn't really matter, but I would say keep it up here. This is where we expect it. And by the way, after this, we will no longer be looking at these. We are going to be moving forward with the symbols. I think in this in digital circuitry, this you can buy as a chip, as a thing, a component. So you don't really need to worry too much about what is inside. But in class, we try to look at what is inside just to enhance our understanding. But in the real world, you would go and buy this and it would look exactly like that. You wouldn't need to worry what is inside. Yeah. Okay. Allen, the timing diagram, as I said, is quite simple. This is the truth table. You set by putting that to a 1 and you reset by putting that to a 0. And if you remember from these diagrams, you can see, for instance, from this diagram that when we put at time t equal to 0, we make S a 0, that makes the output a 1. And even when at t1 we move S back to 1, the output actually remains a 1. So you need to remember that on this timing diagram, sorry, I think it is here, we are initially 0 until we look for a point where set is put to a 1. Set is put to a 1 at that point, so we need to go to a 1 state. Even when set goes back to 0, we remain in that state, and that is the memory concept of the flip-flop. We will remain in the set state until we are cleared. At this point, we are cleared. So if you clear, Q goes back to 0. That's the meaning of clear or reset. Q goes back to 0. And it will remain 0. Even at this point where we clear again, if you are already in the cleared state and you clear again, yeah, you remain cleared. So we will remain at this point until we set again. That's why I was saying that Q equals 1 remains set. And by this, I mean Q equals 1. It will remain set, meaning Q equals 1 until it is cleared, okay, or reset. And if you are in Q equals 0, you remain until set, okay? So that's why at this point, we just remained 0. I don't even need to worry about this. I just draw a 0 until I find a set command and I set. And I will remain set until even if I have another set here and another set here, it doesn't matter. I will remain set until at some point I'm cleared, in which case I go down there, something like that. So I hope that gives you also some sources interchange positions. of the set and reset inputs for the NOR gate latch. Yeah, but don't worry too much about that detailed diagram. Let us just continue so that we don't waste too much time. But you need to remember that the NOR gate latch, these are the details you need to remember. They are active high, so that is S, that is R, there are no bubbles. And here that is your Q and Q inverse. And this is the NOR gate latch. Set is equal to 1, we set. When R is equal to 1, we reset. This is exactly opposite of the state that of the NAND gate latch. Okay. Let us try and continue and look at the applications. So I have the whole diagram here actually for you. So the whole question for you here. So you need to read. Now I don't teach transmitters, so don't ask me transmitters. But it really says that you have a simple circuit that can be used to detect the interruption of a light beam. And the light is focused on the phototransistor. This is a phototransistor. This is how it operates. Phototransistor with light, resistance reduces. Okay, this is how phototransistors operate. Or photosensors, so to speak. If you put it in light, if there's a lot of light, its resistance will reduce, and we know that when resistance reduces, it conducts. You know this thing called V equals IR. Okay, so if resistance reduces, the voltage or the current has got to increase to keep the voltage the same. And if you remove light, like in the dark, the resistance will increase. I think it's something like that anyway. If I'm wrong, you can correct it later, but I think it's something like that. Certainly, that's how light sensors work. So the light is focused on a phototransistor that is connected in the common emitter configuration to operate as a switch. Assume that the latch has been previously cleared to the 0 state by momentary switching or opening switch SW1. If we look at this thing, this switch is connected to the ground. Okay, that means that the state at this point is a 0. Now, what does a 0 do? R is this? I don't even know what this latch is. Let's just take it as the NOR gate latch. I think so, because it is active high. So if you open switch SW1, what happens? If you open this switch, you know, the 5 volts now flows into R, and 5 volts is bit 1. And when R is equal to 1, we know that Q becomes 0. Okay, if you want to look back again at this thing, if R is set to 1, Q will become 0. So that is what they are saying here, that we cleared the flip-flop by momentarily opening switch SW1. So let's say now they have closed it again. Describe what happens, because by momentarily, even if you close it again, it will remain in Q equals 0. Now you look at this Q is connected to the alarm. Q is active high. So that means that Q is equal to 1, sets off the alarm. Yeah, so if Q is 0, there is no alarm. So they want you to describe what happens if the light beam is momentarily interrupted. Now, when there is light here, we have said that the resistance will reduce. So that means that the signal that is flowing from up here is going through. That means if the resistance here reduces, it means that you have current flowing into the ground, meaning that this is a state 0. If there is no resistance on the phototransistor, that means essentially that S is connected to the ground. When S is 0, we do not set. We do not set. Basically, that's what it means. Now, let us assume that the light beam has been momentarily interrupted. What does that mean? If we interrupt it, it means that resistance increases. If resistance here increases, it means that the state here, if there is a lot of resistance here, you have a potential difference. I don't know if in first year or second year you have studied these things, but it means that actually if resistance increases, this voltage V naught is basically increases, and maybe here you have maybe 4 volts, and the 1 volt would be the potential difference across this, maybe even 5 volts depending on the resistance, that one. In other words, the moment you interrupt the light and this resistance increases, there is no path for the signal to flow into the ground because of the resistance. So naturally, the signal will flow into S. That means you're making S a 1. You're making S a 1. Remember that we had cleared this by momentarily switching off or opening switch SW1. By momentarily, it means we have put it back. Essentially, that's what I would say. But even if maybe here you need to keep it cleared so that you need to switch it back so that this goes back to a 0 state. Every time we clear or set, we momentarily perform that function, or we momentarily change the state of the set or reset, depending on what we're trying to do, and then we put it back in its normal resting place. So if this was opened momentarily, it means that it has been closed again, meaning the state here is a 0. But because we have interrupted the light here, the resistance of this phototransistor has increased, meaning that now the natural path for the current or the voltage or the signal is into there, and that is S is equal to 1. That means S is equal to 1 will set the flip-flop. Now, because now Q is equal to 1, alarm goes off. Goes off or goes on, I don't know. This is English now. But if it goes off, what I try to mean here is that it actually starts doing its notification. It starts making the noise. That is an alarm going off, which is quite funny because you would imagine it goes on. Anyway, now we have been told that the light beam is momentarily interrupted. That means that eventually the light beam is restored after a moment. When it is restored, this connection is put back, meaning that the resistance reduces and now the current can flow into the ground. When that happens, S goes back to 0. Okay, S goes back to 0, but by S going back to 0, it doesn't change Q, because S equals 0 doesn't reset. It doesn't clear, sorry, the flip-flop. So in fact, in this circuit, the alarm will go on, or the alarm will go off. I don't know. Can we say the alarm will go on? By that means it will start making the noise. This alarm will start making noise, and it will continue making noise even after you have restored the light, until somebody resets it. And by resetting, you use that switch. So think of this in a practical sense. That you have your phototransistor, and maybe it is around the gate, and you have people, and maybe it's a light beam across the gate. You have a light source on this one side of the gate, and your phototransistor on the other side. It could be like a laser, and your light is moving from its source into that phototransistor, so that at all times it is kept in the Q equals 0 state. Now, the moment somebody comes and passes through the gate and interrupts that gate, presumably an intruder, a thief, the alarm will go off. Or in other words, it will go on. It will start making noise. And even if that person crosses or even runs back, the alarm will continue until presumably the owner of the house or the gate or the security personnel have cleared the compound and made sure there is no issue. And then they can come back and reset that alarm. When you reset, that's when the alarm will go off, will stop making noise. Okay, so that was a long explanation. Any questions? Okay. If there are no questions, let's continue. I imagine that everyone has understood that.
Like me, I was asking about how, like on the transistor, how we are setting for the set part, how we are making S to be 1 and S to be 0. If you don't mind, you can pardon for me.
Okay, I will do that, don't you worry. Let me just create a new slide. So you understood the reset. Let me, sorry. All right. Right. So one more time, 1 minute this time. Let's see. Chichoncho, yes, if the voltage increases, that is the voltage going into S1, yes, then S becomes 1. You remember that these are digital inputs. So below maybe 0.8, it is bit 0, or you know, above that in this range, it is a 1. So that's where that comes from. Brinton, I'll come to that. So anyway, for the guy who was asking, so I said that when the resistance, when you have light, resistance is low, very low. So in other words, if there is no resistance here, then there is no potential difference. And essentially, it's similar to you have connected this line straight to the ground if there is no resistance. That means that in that case, low resistance, S will always be 0 because it is essentially connected to the ground. It's almost like that part is not there. Now, when you switch off the light, you interrupt the beam, resistance increases. Now, when resistance increases here, what it does is that it is increasing the voltage V0 here. So in other words, you have a resistor here, and so there is a potential difference across it, meaning that the voltage at this point, which is V0, increases. V0 increases. And I try to explain it in a simple way, but what we know that current follows the line of least resistance, yeah, naturally. So if there is a lot of resistance created here, the current will basically enter that, and the voltage between this position and the ground is what we call the potential difference across the phototransistor, but it is like a resistance in this case. In other words, V0 is what is that potential difference across the resistance here, and V0 increases as this resistance increases. It's like a potential divider. If you've seen, first years have also done, I don't know, because of COVID, I don't even know which semester this is for you. But if you've seen a potential divider, you know that if this resistance increases, the potential difference across it will also increase. Now, at some point, V0 increases beyond the indeterminate region. Remember, we have an indeterminate region here, beyond maybe 2 volts. If this is 2 volts or 2.4, depending on what technology, once you reach beyond 2 volts, now S becomes 1. And when S becomes 1, it sets Q, and your alarm will start making noise. For Brinton, let's see. So what are our inputs, basically? The truth table. He has asked a very interesting. I mean, I could say with light. Let me do this again. So our truth table could be like condition, inputs, Q, something like that. Low resistance, which means with light. Our inputs will be S and Q. S will be 0, and of course R, not Q. R is also 0 because we have closed the switch again. So that essentially connects that line to the ground. And Q is a 0 in this case because it was, remember, it was initially cleared to 0 and no alarm. That's what it means. And high resistance in the dark, S goes to 1, R is still 0, and Q is set to 1, and you have your alarm goes on, okay. And obviously, the other thing is that, again, if you are moving this in order, if you come back to this state, alarm will go on until it is cleared, until it is reset. bias current generator. I don't know what Hisham you mean, but this light is just light from outside. So I can get my torch, this flashlight or your phone, and you light on this thing and it would. So this is a light sensor essentially. This is how light sensors work. You know, how does a sensor tell you, like these traffic lights that come on at night by themselves, the moment they detect that there is darkness, they will come on. Even if it is during the day and there is a solar eclipse, for instance, it will come on. So this is really a light sensor. Mugabo? Joel?
Yes, sir. So in the case that the beam is interrupted and at the same time the switch is opened whereby we are resetting, what will be the practical behavior of the alarm?
You are basically trying to set and reset at the same time. We have already said that this is invalid, but we are, you know, if you want to do it, we are going to find actually that you shouldn't try to reset and set at the same time. But usually what will happen is the first thing that happened. So you could set, meaning the reset, you could try to do them both. But if you set first, you know, even if it's a moment, if you set first, the alarm will go off. But the moment you try to reset also, meaning the resetting has come in second, then the alarm will go off again. It will be on momentarily. Now, if in your performance of those two duties, you actually reset first, the alarm remains off, but then you set and it will go on. Pascal?
Yes, thank you, Doctor.
Now is making noise for us.
Now,
yes.
My question is that according to the table we are having, input CS and R, when they are both at 0, I'm seeing as if, okay, is it that there is no change or it goes off?
There is no change. You see, when S is 0 and R is 0, it is no change. But remember, we have been told that the alarm was initially, the flip-flop was initially cleared, meaning the alarm is off. So the no change simply keeps the alarm off until we set it. Yes, I thought another hand had come up, but guys, let's move on. I see we are about to finish an hour. So let us look at a case study. This is an interesting case study, and it's almost like it's like an enable circuit, essentially. Here we are using, this is an NAND gate. This is an NAND gate latch, this part here, which is shaded. It is not NOR, but NAND, I think you remember, because this gate is essentially a NAND gate, if we do the alternative. Now we know, and you can, this tells you that these are active low, anyway, because they have bars. Now the outputs, the output Q goes into gate Z2, which is an AND gate, and output, the inverted output goes into another gate Z2, which is also an output, an AND gate, and the other inputs into these AND gates come from the same source, which is a pulse. A pulse is like a square wave, a 1 kilo, in this case, a 1 kilohertz square wave. So we see that essentially what this means is that if Q is equal to 1, if Q equals 1 here, then XA will be equal to the pulse. That's what it means. Okay. Because if you have a 1 going into this point, then whatever is at 1 will go through that. So that's why I said it is like an enable circuit. And if Q inverse is equal to 1, meaning that Q is 0, because if Q is 0, then output here will be 0. Yeah, we can say XB is equal to 0. If Q inverse is equal to 1 here, that means Q is equal to 0, fine. If this is a 1, then whatever is at 4 will go through that, and that what is at 4 is actually the signal. So XB will be equal to that pulse, whereas we know that XA, because Q inverse is a 1, Q is a 0, we know that XA will be equal to a 0.
Programming.
Semaganda. I have to remove you guys from my lecture. So basically this truth table is instructive. You have the switch position. You can see here, the switch is connected to the ground, meaning that if the switch is connected to A, then point A is a 0. If switch is moved to B, then point B becomes a 0. So if we connect it to A, this 0 goes into the set, and obviously B is not connected to the ground, so its output will be 0. So we can save like position A. We can say S is equal to 0, R is equal to 1. Okay, that means we set, because remember this is the NAND gate latch. If we set, that makes Q is equal to 1, Q inverse equal to 0. And if Q is equal to 1, we've already said that XA equals the pulse and XB is equal to 0. Because Q inverse is 0, so it will make everything here 0. At position B, it is the inverse, it is the opposite of this. If we connect this to position B, S will be equal to 1 because it now S is connected through here to 1. R will be equal to 0, meaning we reset or we clear. If we reset, Q is equal to 0, Q inverse is equal to 1. And we know that if Q is equal to 0, XA becomes 0, XB is equivalent to the pulse. So that is very easy, isn't it? Yeah. Okay, let's move on. Now we have the same circuit, but this circuit has an issue. All right, so we are going to see what the issue is. Now, let us look at when it is in position A. If it is in position A, we expect set to be 0. Set is 0. Okay, that's good. We expect the reset to be 1 because obviously it is not connected to the ground. So that's okay. Now we expect Q. If we set, setting makes Q1. Unfortunately, Q is 0. Okay, so this is a problem. Let me put an X. Q is supposed to be 1, not 0. I hope everyone can see that. Then Q inverse, if Q is here, we are supposed to have Q equals 1, Q inverse equal to 0. But Q inverse is a high. Oh, that is also a problem. And we know that if this is faulty, then whatever happens on this side is faulty, because now X should be pulsing and XB should be 0, but they are the opposite. Let us look at position B. At position B, we expect S to be high, okay, because it's no longer connected to the ground, so that's good. We expect the reset to be 0, which is good. It is low. But now, because we are resetting, we expect Q inverse to be a 1 and Q to be a 0. So Q is still 0, okay, so that's good. But Q inverse is a 1. That is also good. Q inverse is a 1, that is also good. Meaning that now XB will pulse, because if this is a 1, the pulse signal will go through. XB pulses and XA is low, so that's okay. When we are setting, Q goes low. You are confusing me, Pascal. Every time we set, in whatever latch, we are making Q equals 1. We are forcing Q to be 1. That is the setting state. It's just that in the NAND gate latch, for you to set, to make Q equal to 1, the set input is a 0. So that's where you're getting your confusion. Okay, so we see that there is a problem around here. The inputs into this Z1, I'll call it Z1 with inputs 1, 2, and output 3. Okay, just to differentiate it from that one. Z1 clearly, around Z1 is where we have our problems. That is where our problems actually just give me one moment. Somebody is here. Somebody that I cannot refuse to see. Just a moment. Okay, so some of the issues could be, you see here, Q is supposed to go high, but doesn't go high. If this Q, okay, Q should be high, but remains low. And we see that for the contact of B, there is no issue, meaning this gate is actually fine, but remains low. What could cause Q to remain low? Z1, the output 3, could be internally shorted to the ground. Okay, meaning you have an internal short here to the ground, meaning that this will always be low. The same could be happening at here, this point here, meaning Z2 could be internally shorted to the ground, okay? Because if you short here to the ground, it doesn't matter what is coming out of here, everything will go into the ground. Another thing that could force Q to 0, because you see Q is also connected to here. So you might find that actually Z1 4 is internally shorted to the ground. Because if this is always a 0, then obviously that line will always be a 0. Obviously, Q line could be shorted itself, not internally, because for it it's exposed, could be shorted to the ground. So all of these are circumstances. But what we have done here in the troubleshooting example is we've isolated where the problem is, and then we have looked at some of the cases that might cause that problem. And then you can find a solution here, in which case you could replace Z1, the gate Z1, the upper gate, and you see if things perform better. If they don't, you can also come to this one. If things don't improve, then it means you can change also that one. So this is how we troubleshoot, and how we find out what these signals are is we use some equipment in the lab. There is a probe we looked at in the lab that you can use to know the states of these. Any questions? Maybe not. Okay. I'm going to give you, if I need to find a cup of water. So I'm going to give you just 3 minutes. I should be back at 10 past, and then we continue. Have a quick break. You can also take a cup of water. Okay, I'm back. Let us use 1 minute to answer this question, and we'll continue with our lecture. Please hurry. We are left with about 20 seconds. You see, with this, you need to at least give me an answer, because I give marks for attendance. And so if you fail the question, at least you can get a couple of marks for attending. And so make sure you don't end the poll before you make a choice. Hey, we've gone into the other minute. Guys, please. I'll be ending this in 10 seconds.
So I can't see the.
You guys, I need to end this, and yeah, I know when I end it, we are on to 156, 157, 158, 159,
Excuse me, sir, I can't see the poll on my screen.
Yeah, a lot of others can, so I don't know how I can help you really, but the others can. So you should be able to see the poll results. And I've ended the poll, of course. 84% of you have answered. And the majority obviously are correct. 71% of you have passed the question. I said that the SR latch is actually when S and R are active high, and that's for the NOR gate latch. So we set when S is a 1 and R is a 0. Some of you chose S is equal to 0, R equals 0, and S equals 1 and R equals 1. We know that S equals 1 and R equals 1 is invalid because you're trying to set and reset at the same time. And S equal to 0, R equals 0 is no change. The many people who chose S equals 0, R equals 1 obviously confused this with a NAND gate latch, but I actually mentioned it that when we say SR latch, we mean the NOR gate latch. I mentioned it in this lecture. Okay, let's carry on. Let us look at something that we should have, we already know essentially. So there are a number of points here, and I've mentioned them here on the side that I want to go through. First of all, the idea of pulses. These are digital pulses. When we say that a pulse is positive, we mean that it was 0, it is moving to 1. So a pulse that was initially 0 and is going to 1 is a positive pulse. A negative pulse is a pulse that is moving from 1 to 0. So for instance, this is a positive pulse because you can see it was initially 0, it went to 1, and obviously the pulse is complete. Whereas this is a negative pulse because it was initially 1 and it went to 0. Now, pulses do not move from 0 to 1 or 1 to 0 like this. It is not momentary, it is not instantaneous. They actually, in reality, they are more like this. When the signal is increasing, time is moving. So even here on this side, it will be like that. It is moving, changing from high to low while time is moving. So it's never, this sharp thing. But in class and whatever, we just use this but in reality, it moves as time moves, and so it is actually slanting. Now, before I talk about the transition times, let me first talk about when we are moving from 0 to a 1, it's at this 50-point percentile that we say that we have moved from 0 to 1. Across this whole edge, this part, we are still bit 0 until we cross the midway point. So if I have my pulse like this, of course it is slanting, okay? While my signal is still at this below half, I'm still bit 0. And the moment I cross beyond half, I'm at bit 1. Now, another thing, the rise time is the time between when the signal is at 10% and 90% of the maximum voltage. So if it is, say, 10 volts, let's say that this point, this is actually 10 volts. So, the signal will have started from 0 volts. It increases towards 10 volts. So the rise time is the time it takes the signal to move from 1 volt to 9 volts. Because 1 volt is 10% of 10 volts and 90% of 10 volts is actually 9 volts. So we don't really start measuring rise time from 0. We start from 10% and stop at 90%. That is the rise time. And so if I have my slanting thing like this, and that's 10% and that's 90%, then my rise time is that. And the fall time is essentially the same. It is the time it takes the signal to fall from 90% to 10% of the maximum pulse voltage, which in this case starts from here up to 10% there. That is your fall time. Okay, so I've talked about this, I've talked about this, I've talked about this. Yeah, this contains that. Now, when the signal is transitioning from either a 0 to a 1, the first edge of the pulse is the leading edge, okay? First edge. And the trailing edge is the second edge of the pulse. So like in this case, this is the leading edge, and this is the trailing edge. So you have a pulse, that's the leading edge, that is the trailing edge. We don't work with leading edges and trailing edges a lot, but technically we can talk about them here. This doesn't work only in this case. It can also work for negative pulses. So this is still the leading edge much as it's falling, and that is the trailing edge much as it is increasing. Jordan, what do you mean? What do you mean does this have practical? And then we talked about pulse width. Pulse width is the time. So width in this case is time, not distance. It is the time between the 50% points between the leading edge of the leading edge and the trailing edge. So the time between the 50% points of the leading and trailing edges of the digital pulse. Obviously, this digital pulse, we are about to start using it with flip-flops. It is very important because it is the one actually that sets most of the stuff that we are about to look at in motion. Without digital pulses, we are not going to get far with some of the flip-flop work that we are going to look at. In real life, you're about to see, you're about to see, but also, this is actually essentially similar. So if you are looking at this pulse that we are talking about, it is not, sharp like this. It is more like, and so on. So for instance, technically speaking, you want to have low rise time, low trailing fall time. The reason is obviously you want your the pulses to be as sharp as they can, and so the rise time should be very narrow and the fall time should be narrow. And essentially in real life, these are around a few nanoseconds, 5-10 nanoseconds, so they are not really long. The other thing is that if you want a fast system, then you want very narrow pulse width, okay? that because the path width gives you the concept of a period, and the period goes into frequency, because we know that frequency is 1 over the period. So if the period is small, the frequency is high, and your system is faster. These are some of the implications I'm talking about that I think Jordan was asking about. But I guess by normal, Jordan, I think by normal you mean sharp edges. Again, that is just a software. It is a simulation. It's not real life. But in real life, my signal is moving from 0 volts to 5 volts. You know, that's how we are moving the state. You don't expect this to move in an instant. It is not just pressing a button. The voltage actually increases, and as it increases, obviously the time is moving, so it is more of a slanting thing. It affects speed, it affects different applications, and so it does have some implications, in fact. Yeah, I could leave this example to you because it's in the book and it's really easy based on what I've already explained. Y-axis is voltage. Okay, remember that we are using volts, so we are moving from state from 0 to 5 volts, where 5 volts is VCC and 0 is really ground. Some of these VCC can be 3.5 depending on different, but usually we use 5. Have we looked at before? We've looked at this stuff before. But this is a signal, so it is a voltage. You can see here you are looking at 4.5, which is really 90% of 5. This is 0.5, which is 10% of 5. And so they've given you different bits of information here and asked you to draw this, so you can look at it later and draw it. But you can see time is in nanoseconds. So these are really narrow. They shouldn't worry too much. So another thing that I want to look at is our clock signals. In fact, clock signals are made up of these digital pulses that we've been looking at. A clock signal is essentially a rectangular pulse or a square pulse. And these are used in clock flip-flops. So use clock flip-flops. The flip-flops that require a clock to perform, and we are going to look at them in a moment. So without these clock signals, you would not have a clocked flip-flop. You could perform the flip-flop would not work. And so again, this is important in real life. Now, we have two kinds of operations, flip operation. One is synchronous, the other one is the synchronous. So let me start with the synchronous. Synchronous flip-flop. These are flip-flops whose outputs change, even of course based on the inputs, on at predetermined times. So even if the inputs change, the output will not change until a certain time. Okay, so let's say that I have, for instance, remember when we had, I have S and R. Essentially 0. This is S, R, and Q is 0. So if I make S1, Q will simply be set. It will become 1. This is an S flip-flop. It's Q inverse. But we are saying that for synchronous flip-flop, if S equal to 1, this Q will not change until a certain time has reached. So there is that kind of things happen at predetermined times, and then nothing happens until the next predetermined time, and nothing changes until the next predetermined times. Now, for synchronous flip-flops, these ones do not work based on time function, like a time guide. For the moment inputs change, the outputs change. Therefore, it goes without saying that the SR, the NAND latch we've looked at, are asynchronous systems. The output change the moment one or the inputs change, if those inputs obviously change. These are difficult to design. They are synchronous. They are the outputs change at predetermined times, and these times are actually determined by the clock signal. So if the clock signal is like that, we can say this is pulse 1. These are pulses 1, 2, 3, 4. So every time there is a pulse, something can happen. Every time there is a pulse, something can happen. Before that pulse happens, nothing can happen. So saying synchronous systems happen at predetermined times. So like when we are in our normal state and we are saying, okay, we are sync, like discussing something, you're on the wavelength, or we are in sync. It means you are moving together. You are sort of same sort of loop. And people use wavelength, even know what it means, but you can even trace it to the concept we're talking about. Let me look at this question. I've failed to access post so far, yet I'm ever on. Yeah, same. Others access them. So I don't really know how I can help you, but maybe you should help how to access them or change the device you're using. So the clock is important, its frequency is important, and so Rwanga, if you next time are just from the picture. So of the clock is the cycle per second. So basically, if the frequency is high, meaning the clock is faster, these things are happening, your system is fast. We're going to be looking at this. And so when we have flops, we use we apply our clocks to, we call clock flops. In fact, most of these flops are edge-triggered. Let me tell you what that means. Let us look at our digital pulses again. Our digital pulses, this is actually a rectangular and a square wave. So it can be either or. These are digital pulses. These are the signals that we are talking about. And what they do is they just keep changing from 1 to 0 back to 1 to 0 back to periodic. So these are periodic signals as well. Right? I think everyone knows what a periodic signal is. By saying that they are edge triggered, before I explain that, let me just say that when you look at this, this is a positive pulse, because it is moving from 0 to 1, and so they are moving from 0 to 1, they are positive pulses. But more than that, the edge, the side of the leading edge, the edge in this case is this edge. We can see it is moving from 0 to 1. We say that it is a positive going transition. Positive going transition. And this side is NGT, which is a negative going transition because it is moving from 1 to 0. So we call it an NGT. Same here. This is a PGT and this is an NGT. We are not so interested in this part here. Now, why is this interesting? It is because we have said that our clock flip-flops are actually edge triggered. So we can say that this clock flip-flop is actually PGT or NGT, or uses a PGT or NGT clock. What it means is that if we say that it is a PGT, it means that it is triggered by the positive going transition. If it is NGT, it is triggered by the negative going transition. So it means that this, let's consider a PGT. This is the position at which things happen. In other words, if you've changed inputs and maybe you want to set, your flip-flop will wait until that position where then until that time, not position, until that time where it can now set for you. And the negative going transition will not have an effect until the next one, PGT. So we are only looking out for PGTs. If we had said that our clock is an NGT clock, it means it is edge triggered, but on the negative going transition, NGT. So we don't consider this. We are looking for the NGT, 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 and so on and so forth. So clocked flip-flops are edge triggered. There are some systems that are triggered by the base of the signal, but those are not common and we are not going to really look at them. But we are interested in edge triggered flip-flops, and those are triggered by either the positive going transition or the negative going transition. So similar to the NAND gate latches, where we were saying that once you are set, you cannot be the only change that can happen is when you reset. Here, if I check this PGT, I don't care what happens in this side until I reach the next PGT. I don't care what happens here until the next PGT, and so on and so forth. I think there's a question. Jordan, synchronous. Okay, so this stuff, maybe you need to go and read in the book, but when we start doing examples, it will be quite clear to you. So synchronous systems mean that yes, you have applied changes at the inputs, but those changes will not create a change at the output until a certain time. And now we know, after explaining this, that that time will be either at the next PGT or at the next NGT, depending on which active transition of the clock or active edge transition of the clock you're considering. So sometimes I say active clock transition. And what I mean here is that I mean either a PGT or an NGT, okay? Active clock transition. It is either a PGT or an NGT. Okay, so let's continue, and we look at a few examples, and I think they'll give some of you who are confused a bit more information. So this is these are models of the flip-flops, and you can see that this flip-flop is different from the flip-flops we have looked at before. Now we have what we call control inputs. In fact, these are like your SR. These are your like SR, but we don't call them SR here. We will call them something else, but they are like S and R inputs. And then the input that we did not have before is the clock. We didn't have the clock before. We usually say CLK. Sometimes we can say CP, where this is clock pulse, and so on. Can even write it in full, but CLK is usually common. We still have our two inputs, the normal output, two outputs, the normal output and the inverted output, and then we have a clock. So we draw the clock like this. If you have your flip-flop like this, we can draw the clock like this, you know, so that is a clock. And we have clock, you can write it outside, it doesn't matter. Usually we draw the clock like that. So if you see a clock with an arrow there, I don't need to tell you that this is a PGT. It just tells you that actually the active transition is the transition from 0 to 1, which is a PGT. You can see here that if we want an NGT, we need to add a bubble, and that bubble says negative. So, you know, we've been using bubbles for meaning active, low, and so on. So if you see a bubble, this is actually an NGT. I don't need to tell you, but sometimes you will see something drawn like this, but in this case, the arrow will be there. This arrow tells you that we are moving from a 1 to a 0, so that is a negative going transition. Here, the active transition of the clock is PGT. Here, the active transition of the clock is the NGT. Sometimes, actually, most of these we have two inputs as well. So you can have your input 1 and your input 2, and you can have your Q and Q inverse, and usually we have the clock in the center, okay? And this clock in this case is a PGT. These arrows are important. If you draw your thing and you don't put arrows, I'm not going to give you any mark for that. Okay, so the arrows are important because they tell me, okay, this is a PGT, this is an NGT. Okay. Okay, so so let's look at an example of a clock, of a flip-flop. Or before we go to a flip-flop, there's something small here, and I've tried to write these out because they are quite confusing. So the setup time, these are synchronous control inputs, and you have your clock. So basically, for you to change something, you should apply inputs first. And once those inputs have been applied, then you can set the clock, okay? In other words, give the clock pulse at which you want your inputs to perform a change to the output. So in other words, your signal your inputs should change first before the clock, because the clock is the one that sets everything in motion. So now if you first give the clock before you change your inputs, nothing will happen. You just keep the previous state. So we apply the inputs first, and then we set the clock. Now the difference between these two events is what we call the setup time. In other words, once I change my inputs, I should leave a certain minimum amount of time before I give the correct clock transition or the active clock transition. The reason is that when I change my inputs, I set them to 1, for instance, they will take time to get to 1. And even when they get to 1, they are a bit unstable. They need to stabilize. Remember, these are voltages and currents, and they are resistors, and there are so many things changing. So I need to give my signals, my new inputs, a bit of time for them to settle down into their new states. And then after that, I can give the clock transition, and you can see it here. So you can see then that the setup time in this case is the time interval immediately preceding the active clock transition. Preceding is previous. The time interval immediately preceding the active clock transition, during which the control input must be maintained at the proper level. That means you set it to 1 or 0, depending on whatever, and then you give it a bit of time for it to stabilize in its new state. If you do not meet this new requirement, the flip-flop may not respond reliably, because the signal, the state may still be unstable, and so it may be up and down, you don't know. The hold time is the opposite. The hold time in this case is the time following the active clock transition, during which the synchronous control input must be maintained at the proper level. What this means is that even after you have applied the clock, those inputs should be maintained at that level for a bit of time, because even when you apply the clock, it might take a bit of time for the effect of the clock to set things in motion. And so if I'm applying my clock here, I should make sure that I make sure my inputs have settled in their state. And even after I have set the clock, at that point, I should maintain those states until a certain time. And so this time here is the hold time, TH, and this time here is the setup time, TS. Hold time means hold things as they are for this time. The setup time is set things up and wait a certain moment before you give the clock transition. So I think that is quite clear to you guys. Okay. So if you have no questions, let's continue. So let us look at the clocked SR flip-flop, okay? So we have looked at the SR flip-flop. Now this is the clocked SR flip-flop. And we already know that SR is active high. So all we have done here is we have added a clock. And this clock triggers on the positive transition. Okay, so you can see the arrow is on the PGT. If it was on the negative transition, the arrow would be here and we would have a bubble. If we look at the inputs, now we have added an input of the clock, but the rest is the same. 0, 0, no change. We already know that. 1, 0 sets, that's a 1. 0, 1 is the reset, and that is ambiguous or invalid. Now, what we have added is the clock. So, the clock, the inputs are just the positive going transition, which is an arrow pointing upwards. That just tells you that actually these things happen after that clock transition, after the positive going transition, the PGT. And without this, we would not see this stuff. Let me see what's in the question. What is the use of hold time? Hisham, it's like, I have applied something, but I need my inputs to remain stable for a certain period to allow the effect of the clock to happen reliably. Imagine when you set your alarm, imagine when you set your clock, immediately you change the inputs. That would be similar to like you're driving out of your gate, and even while you are still driving over the gate, somebody is closing it, it might hit your car. So in other words, you give a bit of a lag for the clock transition, the active clock transition to actually perform its functionality. That is really the importance of that. Okay. So this one really hasn't changed anything. The inputs are the same, the outputs are the same, but what we have added is that's the clock input, and it needs to show an arrow upwards. If we were showing downwards, this would be NGT. Now let us look at this. This is the timing diagram. S is 0, R is 0, and we have been clearly here, we are being told that Q is initially 0. So for us to make Q a 1, so Q will be 0 until we set. So this is the same. Now, we have a clock signal, and you can see the clock signal is just, in this case, it is a PGT. So we don't care for these arrows. These arrows are not important, and they shouldn't even be here anyway. Or in other words, you don't have to put them. I only have interest in the active clock transition, in this case, a PGT. Now, let us see. We have S equal to 0, R equal to 0, and Q equal to 0. At this point, we are looking at the first PGT. At the first PGT, which is point A, we are looking at what is the state at the input. The state at the input is 0, 0, meaning no change. So if we were at 0, we remain at 0. Now here, I don't care until I reach the next PGT, which is there. You see here at this point, we change S to a 1. If that were the case, it would be at this point that we actually set. If this wasn't a clocked flip-flop, and remember, this is an asynchronous clocked flip-flop. Asynchronous flip-flops are not clocked. This is a synchronous operation. So in fact, we don't set here. We have to continue until, yes, we have seen that the input has changed, but we have got to wait for the clock transition, in this case, the PGT. And when the PGT happens, we look at this. Okay, that's a 0, that's a 1. That means we actually set. And so then I can just continue until I reach the next PGT. At the next PGT, I see, oh, okay, now I have a reset at the 1 and set at 0. Okay, so I should reset because this is that state. And then I can change all the way to the next PGT. In other words, I don't care for these. Before, we were looking at the transitions in the inputs. Here, what is of main interest is actually the PGT. Where is the PGT? So here I can continue all the way to the PGT, and I check the inputs. 0, 1, it means I set again. And then I can continue all the way to the next PGT, which is 0 again and 1. And I set again, I remain set really, because I'm already set. So the difference between these clocked asynchronous flip-flops and the ones we have seen before is that the ones we have seen before are asynchronous. That means that when the inputs change, immediately that can cause a change in the output. But with synchronous or clocked flip-flops, even if you have changed your inputs, you must wait until the active transition of the clock. In this case, it is the PGT, and then you can, the effect of those inputs can actually be reflected at the output. Is there a question? Is there a question? I thought there would be a question. Either you are too lost, or I'm a good teacher, or you are tired, maybe. But if there are no questions, let us go on and look at Ramon or Ramon. Yeah.
I'd like you to help me and clarify if the clock, the direction was going downwards, how would the waveform be?
Oh, fantastic. That's a good question. Let us look at what would happen. Now, in this case, if we had an NGT, and I'm going to draw my NGT somewhere up here. If we had an NGT, we are at 0. Okay, so let's say we are at 0. But now I'm interested in the NGT. So I'm interested in that position. At this position, I check. I have a 0, and maybe that's a 1. So I can set. Okay. and then I'll go all the way to the next NGT. At this NGT now I have a 0 and still a 1. That means I remain set all the way to the next NGT. Now I have a 1 along here. I have a 1 at that point and a 0. Somebody's giving us an echo. And so I have a 0 here. So because I have a 1 on reset and a 0 on set, now I can do what? I can reset. And I'll go all the way to the next. In other words, I don't need to know what changes in the inputs have happened in between my active clock transitions. I'm only looking for the clock transition and seeing what is the current state. This is a 0 and that's a 1, meaning I set again until that J, and I will again set. So I remain set and so on. So you can see that depending on what transition you use, your output is actually quite different. Let me see some questions. Vivian is very lost. Just a recap of okay, I'm going to do that. More clarification, Ivan, meaning the clock is a control signal. The clock, the clock is not a control signal. The control signals are the inputs. The clock is just a synchronous signal. It is that one. It implements the synchronism within the system. Let me do this again. And now, Vivian, you need to pay very particular attention to this. In fact, just a moment. I'm going to. My job is to teach you to understand. Okay, so I'm very happy to go through things again. Okay, so I need to come bring this one also and put it there. So let us assume that we have a PGT and we've been told that Q is initially 0. So let us first do this thing based on the previous cases when we didn't have a clock. And I'm going to draw it here, like previous case, which was asynchronous. In the previous case, if we had a Q equal to 0, it would remain 0 until this is S equal to 1. The moment S goes to 1, we set, sorry, because you can see when S is 1 and R is 0, we set. So it would go to a 1 all the way to when R goes to a 0. Unfortunately, these are sort of matching, but assume they are not matching. So at this point, let us say that S is 0 and R is 1. If R is 1, we reset. And we remain reset until the next point. Let's say here R is 0 and S is 1. The moment S goes back to 1, we set again, and we remain set for as long as S is 1 and R is equal to 0. This would have been the previous case. But in this case, with a clocked signal, if our Q is 0, this is a PGT. I'm saying that even if at this point, I first look at the first PGT. At this point, R is 0 and S is 0, so no change. That means I remain at Q. Now, we see that previously, the moment S goes to 1, we would have set. But here, even if that happens, we cannot set until the clock transition. So it's almost like you hold on until the next set. Do you know when we are praying? You know me, I don't go often to church because of the things that happen in church. But you know when you come to church, I used to go to church those days at campus. Now I go occasionally, so I'm not an atheist. But if you come to like St. Francis, which is where I used to go, and you find people in the church praying, they don't let you enter. They wait for the people in church to stop praying, and then you can enter. It is similar to this. So yes, at this point, the state has changed, so we should ideally set. It's like now you have reached the church, but people are praying. So you will hold on until there is an active clock transition. This is the first PGT. This is an NGT, so we don't care about it. This is the second PGT. So at the PGT, you can check, okay, what is the new state? Now R is 1, is 0, and S is 1. 0 and 1. We know that that will actually give us an output of 1. So Q now will become high. And it will remain high because we know that even if inputs change, nothing changes until the next clock transition. So it will remain high until the next PGT. At the next PGT, we check again. Actually, now reset is 1 and set is 0. So 1 and 0, now we clear. So we can come back to 0 and we remain in this state until the next PGT. We don't care about NGTs. I already said they shouldn't even be arrowed here. This PGT we check again. Okay. I mean, things have changed here, but in the synchronous sense, they don't matter until actually the PGT or the NGT, in this case, the PGT. So at this PGT, now R is 0 and S is 1. Oh, okay. So we go back to set. We set again until the next PGT, which is still 0, 1. So we remain in that state and so on and so forth. It was, if it was an NGT, as somebody asked, meaning Q is initially 0, we are not interested in this state now. We are actually now interested in that point. So we remain, we go to 0 here. At this point, we check what is actually, now let's assume that S changes to 1 at this point. If S changes to 1 and R is still 0, we set at that point. Remember here, we could not set because S was still 0. When S became 1 here, we could not set because we had to wait for a PGT. Now, NGT will go until the next NGT, and we check. This NGT R is 0, S is 1. Okay, so we stay set until the next NGT. This next NGT happens at this point, and here now R is 1 and S is 0. Okay, so we reset now because R is a 1 now and S is a 0. Until the next NGT. This next NGT, R is a 0 and S is a 1. S is a 1, so the moment S is a 1, we set. Vivian, is that clear? Mugume has network issues. I don't know why you say we are on and off. I think you are on and off. The other people are not having issues. So if the clock is constant, there would be no change in output. Patricia, that is true. And I believe that by saying if the clock is constant, you mean that there are no transitions. So if the clock is constant, if you have one pulse forever, yeah, no output would happen, but that's no longer a clock. A clock should be like a square wave or a rectangular wave. Mugombe, Isaac, okay. So we don't do anything at the first PGT. We at the first PGT, I think you mean this one. We actually do something, but it is that just like that S is 0 and R is 0, so it is no change. So we do something, but it is what? It is just maintaining the previous. Senabulia Solomon. In other words, we are following the truth table. Of course, we are following the truth table. Everything we do here, we follow the truth table. Sebakoni, Akram, is the clock providing the setup time? Yeah, the setup time comes from the clock for sure. The setup, the whole time that comes. No, it doesn't come from the clock actually. The clock is the clock, but the setup time and hold times apply to the control inputs. So those, if you know that my clock is going to come in the next 20 nanoseconds, and you know that the requirement for setup time is 10 nanoseconds, you should do it within that time. Okay, so you could say if my clock is 20 seconds away, and my requirement on hold time is on setup time is 10 nanoseconds, I should make sure that in the next 10 nanoseconds, I have changed my inputs. Shakira, it's clear. Vivian, it is clear. Okay, wonderful, nice to know. Okay, I've answered all your queries. And now we have a few minutes left. Okay, complete it. Yeah, so this is the negative one. So this one would do trigger on the negative transition. The signal is the same, but we've actually done this. In fact, we've done this twice. So yeah, so if it is NGT, we are looking at the NGT positions, all right? And we are looking at the current state and drawing the final state. Kichoncho, if I'm to ask doctor, how can they set that kind of question? Do they specify NGT or PGT? Yes, they do. In fact, it will be me setting it. So they will specify, they will tell you in the question that it is an either a PGT.
But because it is me setting it.
Second on the acronym. What are you saying that I'm wrong? We heard you. I'm the one setting it. I set all my questions. And that is a fact. You can't change it. So usually I'll give you a flip-flop with, actually before second on interrupted us, Kichoncho had asked a very interesting and a very important question. So if I've not, I'll say it in the question that it is an NGT or a PGT. If I don't, you will see either the bubble or no bubble. If it is a bubble, you know it's NGT. If it is no bubble, you know it's PGT. Sometimes you also have that. So like this is an NGT. If it was a PGT, it would look like that. Okay, so all these three pieces of information tell you actually what kind of active clock transition we are interested in. If I set you a question and I don't specify the NGT, I mean, then how do you do that? So always it will be specified. Charles?
So I want you to clarify more on this output at point D, because at point D, I see one signal is the set is still up slightly, and then the reset is down. So I thought it was activating at that point.
Actually, yeah, it is because I was doing it in a rush. But now that you have said it, if you look at it critically, it is like, isn't that where we are?
Yeah, exactly.
Yeah. So I was just doing it in a rush, and but if you are doing it critically, yeah, you do the right thing. Don't worry about it. The next NGT is actually through that, and this NGT is there, and that NGT is there. So it's really, you just follow what you see. Sometimes if things are changing at the same time, it can be confusing, but we try to make sure that we don't bring a situation where the inputs are changing at the same time as your clock transition. Obviously, there is a requirement on setup time and hold time, although that requirement really is, these are nanoseconds, so you can't really see nanoseconds on a scale. But technically, you would have a 0 here, until B. B is 1, 0, so you set at that point. At this point, you remain set. At F, you clear. F is here, you clear. At H, you set again, and so on. So it would be like something like that. But I was doing it in a rush here, so then there is Chichoncho. Okay, Chichoncho, I've answered. So, doctor, does this mean that we shall not meet S equals? Yeah, because if you meet that, then that is ambiguous. So I can't ask you to do something ambiguous. That shouldn't happen, and so you'll not meet it. Okay, how do I know people who have attended but didn't submit? And why didn't you submit? Or those are people who didn't see the quiz, I don't know. But if I can prove that you have attended, for sure there are like 10, 15 people who attended that didn't submit, I can give you some attendance marks. I just don't know who you are. Ngobi, maybe I can look I'll figure out, I'll probably find you somewhere. Jerome Ngobi, so I beg that the lecture recording be shared. I'll give you the recording, that's okay. We are coming to Christmas. I don't know what sort of gifts you have prepared, but the reason I don't mind giving you the recordings, and by the way, if you check on the link I gave you now, there are a number of recordings there. So if you don't have recordings, go and pick up those ones that are available. The reason why I don't give recordings is people think they can rely on recordings and not come to class. There are so many things that you learn in class. And also you do things in time. And also for me, it is good to know that most of my students are here. Right now we have, let me see, we have about 116 students. The class, the test that I gave the other day was done by 200 plus students. So you have got to ask yourself, I'm your lecturer. My job is to make sure that you pass. But why should you pass if you don't come to class? So this is the issue. And I don't mind giving you a retake. I really don't. It actually makes me happy if you are not attending class and you get a retake, because it means you have another chance in future to find time and attend class. That is the reason I don't sometimes share my recordings. It's not that I'm a bad guy, you know, and it doesn't matter anyway. So please try and come to class.
Excuse me, sir.
Yeah, but I'm still talking. Can't you wait and I finish? No? Let me see. Yes, you talk since you are.
Like, it's not like we want to miss the lecture, but sometimes you find you have not gotten the concept very well, and then we use the recordings for the review. Like, we want to review what you put.
Of course, I understand that, Humphrey, and I appreciate it. And as I said, I share them. But among us, we have people that are making everyone's work difficult. But I'll give you this lecture recording. I will do that. Don't you worry about it. And as I've said, there are a number of others online that you can check out. Maybe after, when I'm putting this one, I'll delete them. So
Okay,
it's good that you check there. Yeah. Otherwise, I hope my test was easy. I'm told that people were writing and everything was good. So that's nice to know. But if you had any challenges with that test, I ask you really to now ramp up your reading, because the test, the work gets harder. You know, we were looking at the first 3, 4 chapters. Now we are looking at flip-flops. We are going to look at counters in the next few weeks. And so things get a little bit harder. You shouldn't be failing the first cut, because that's a bad sign. We are going to do another test this month, because I'm told you have exams when you return in January. So we are going to have a test around mid-December, right? So I'm just telling you. And that exam will focus on flip-flops, mainly flip-flops, and maybe chapter 4, essentially. So, you know, I'm just saying that things are serious and we need to read. Thank you very much, and see you next. Before you go, I put a quiz online. It is on Friday at 7, I think, at 5, and it will be available to you for 45 seconds. I gave a time limit of 30 minutes. Sorry, it will be available to you for 45 minutes. Sorry. And it's available. Once you start it, you have 30 minutes to complete it. I believe that you can complete it. It has some very simple numbers and a couple of numbers where you need to do some bit of Boolean algebra. But I know you guys have a habit of doing this work together. This is an individual quiz. You actually need to use your head, because in the exam or the test, you'll be alone. Okay, so you could say, let me copy or cheat and pass the quiz, but these quizzes will probably, or tests will probably cater for 20% or 15%. What will you do when I'm asking you to work for the 60% when you are alone? You could see how we set you up in the test. So even with tests, we are very serious. So please try to work alone. Try to use your own head, try to rely on yourself, because it is good training for the final exams and for the tests. And I know that I asked you people who have not enrolled to enroll. I'm told there is a trick people use where a non-student logs in, gets the test, and gives it to you to do, and then you just come in late and pass. That's why I've made the time available very short, because you see, you do something, we respond, and sometimes the responses we do are not good for you. But I'm also going to look through the students. I'm going to go download the students and look through and make sure these are my students. And if you are not my student in this class, please get out, because, you know, I'm going to ask you what you are doing, and maybe you might have to explain that to a panel, to the college or something. Otherwise, have a nice weekend, and let's meet again on Monday. We shall have EE labs on Friday at that time. I put it on Friday at, can I move it to 6 p.m.? Will you still be having EE labs? Okay, I'll move it to 6 p.m. That is Jerome. That's fine. I actually can move it to midnight if you like. I don't care. Just let me know. Have a nice weekend.